Hello friends, subscribers and new viewers of this channel, and welcome to Control Engineering and Robotics tutorials. In this tutorial we explain how to sketch the Nyquist plot of a transfer function by hand. The ability to sketch the Nyquist plot of a transfer function by hand is a fundamental skill that every control or robotics engineer need to have. And consequently, that's why I created this tutorial. Furthermore, the problem of sketching Nyquist plots of transfer functions is very important for investigating the stability of transfer functions and dynamical systems. Consequently, pay close attention to the material presented in this video tutorial. In this video tutorial, we consider a particular example. Namely, we consider this transfer function. This is a second-order transfer function with a single pole at 0. Its Nyquist plot is shown over here. And by the end of this video tutorial, you will learn how to sketch this Nyquist plot by hand. First, we explain the basics and the main idea of Nyquist plots. We start from our transfer function. Then, the first step is to set S to be equal to j omega, where j is the imaginary unit, that is, j is equal to square root of -1, and omega is the angular frequency. Omega is equal to 2 pi over t. By substituting S is equal to j omega inside of our expression for our transfer function, we obtain the so-called sinusoidal transfer function. The sinusoidal transfer function has this form. T is equal to 1 over j omega multiplying j omega plus 1. Our j omega is a complex number. Since j omega is a complex number, our sinusoidal transfer function is also a complex number. And we can represent this complex number as the sum of the real part that will depend on omega and the imaginary part that will depend again on omega. And over here we will have the imaginary unit. To repeat, by substituting S is equal to j omega, we obtain the sinusoidal transfer function, and we can represent the sinusoidal transfer function as the sum of the real and imaginary part. Then we can construct a coordinate system and a complex plane, and in this new complex plane we can plot the coordinates of the points for fixed omega. Namely, on the horizontal axis we can plot the real part of t, and on the imaginary axis we can put the imaginary part of t. That is, for any value of omega over here, we are going to obtain a point inside of this new complex plane. For example, if I pick omega here to be equal to 1, I substitute here, I will obtain certain expression for real part, certain expression for imaginary part, I can substitute 1, and I will obtain a point over here. Let us go now one step back and let's focus ourselves on this transfer function. S in this transfer function is a complex number, and in the general case, S is written like this. Its real part, denoted by sigma, plus j multiplying omega, where omega is the imaginary part. At the same time, omega is our angular frequency. S can be represented as a point in this plane over here. Here's the real axis denoted by sigma, and over here I already sketched the imaginary axis. Here it is. And S is a point over here, for example. Now, by setting S to be j omega, we restrict S to take values on the imaginary plane in this original plane. That is, we are constraining S to be on this imaginary plane. And this is a very important thing to understand when plotting Nyquist plots. S constrains the values, and j omega makes sure that these values are actually on the imaginary axis. So over here in this expression we set sigma to be equal to 0, and our S becomes j omega. The Nyquist plot is obtained by varying omega from minus infinity to plus infinity on this imaginary axis. That is, we will simply vary omega from minus infinity to plus infinity. And what is important to understand that any point over here, for example this point with omega value equal to, let's say, omega star, is mapped to a certain point inside of this plane. For example, this point over here. Namely, I will denote this point by t of omega star. And this mapping is actually performed by our sinusoidal transfer function. That is, by this transfer function. Now, let's summarize. The Nyquist plot is obtained by varying omega values from minus infinity to plus infinity in the original complex plane. For any point on the imaginary axis, we will obtain a corresponding point in the mapped plane. The mapping is performed by this transfer function, that is, by our sinusoidal transfer function that's obtained by substituting S is equal to j omega inside of the original transfer function. And if we take all the points, we can map these points to the corresponding points in this plane. For example, this point can be mapped here, this point can be, for example, mapped here, this point can be mapped here, this point can be mapped somewhere over here. And as the result, we obtain the Nyquist graph or the Nyquist curve, or even called the Nyquist plot in this plane. And this plot can, for example, look like this. Again, let's summarize. Nyquist plot maps the imaginary axis in our original plane to a graph in the transformed plane, where the mapping is performed by the transfer function t. Now, some of you might wonder, what is the purpose of this semicircle over here? Why I simply don't pass through the 0 over here when I go from minus infinity to plus infinity? The reason for this is that at 0, our particular transfer function explodes. That is, it has a singularity, and consequently, in order to properly sketch the Nyquist plot for this particular form of transfer function, we will have to elegantly avoid 0. We are going to avoid 0 by using a semicircle with a very small radius. And this trick will be used to properly sketch the Nyquist plot. Now, I need to use the semicircle in this particular case, since over here I have pollen 0. If you don't have a pollen 0, you don't need to use the semicircle. However, I deliberately picked the example that's more challenging to plot, and I will have to explain how to parameterize this circle and how to sketch the Nyquist plot when we live on this circle. Okay, let's start with sketching. We start from our transfer function, and as explained previously, we substitute s by j omega. And then we substitute this value inside of our transfer function. As the result, we obtain the sinusoidal transfer function that looks like this. 1 over, instead of s, we write j omega, multiplying j omega plus 1. And we close the parentheses. Good. What do we do next? Next, we need to write t of j omega as the sum of real part that will depend on omega, and over here we will have the imaginary part that will depend on omega multiplying the imaginary unit. So how to do that? Well, first of all, let's multiply these terms in the denominator. Let's see, what do we have? We have t of j omega is equal to, in the numerator we have 1, in the denominator we have minus j omega multiplying j omega is minus omega squared, and over here I have j omega multiplying 1, that's simply plus j omega. I can write this expression like this: 1 over j omega minus omega squared. Next, I want to express this whole term as the sum of the real plus imaginary part. To do that, I will multiply both the numerator and the denominator by j omega plus omega squared over j omega plus omega squared. I can do that since j omega plus omega squared in the numerator and the denominator can be simply cancelled. That is, this whole term is equal to 1. Then I will use this trick. Namely, from basic calculus, we know that a squared minus b squared, where a and b are arbitrary numbers, they can even be complex numbers, is equal to a minus b multiplying a plus b. Since over here I will have j omega plus omega squared multiplying j omega minus omega squared, I will exactly have this thing. So as the result, I can write this. In the numerator, I will have j omega plus omega squared, and in the denominator, I will have j omega squared, j omega is my a in this formula, minus b is omega squared. So I will have minus omega squared, then squared. And let's continue to derive the expressions. So t of j omega now becomes, let's see, in the numerator we will have omega squared plus j omega, and in the denominator I will have j to the power 2 is simply minus 1, and I will have minus omega squared minus omega to the power 4. And consequently, from here I can get the real and imaginary parts. The real part will look like this: minus omega squared over omega squared plus omega to the power 4. Then I will have minus over here, and the imaginary part will look like this: omega over omega squared plus omega to the power 4, and let's not forget the imaginary unit j. And consequently, the real part is minus omega squared over omega squared plus omega to the power 4. Now, if omega If omega is not equal to 0, I will simply denote it like this. If omega is not equal to 0, I can divide the numerator and the denominator by omega squared. However, again, the condition here is that omega is not equal to 0. And if you remember, at the beginning of this tutorial, I said that we are going to avoid 0, so this is perfectly fine. And as the result, the real part becomes 1 over minus 1 plus omega squared. And this is the final expression for the real part. Similarly, for the imaginary part, we have imaginary part is equal to minus omega over omega squared plus omega to the power 4. And under the condition that omega is not equal to 0, we can express this part, that is our imaginary part, as minus 1 over omega plus omega to the power 3. Here is the real part once again, and here is the imaginary part once again. Before I start with sketching of the Nyquist plot, I need to introduce a new notation. Namely, in the sequel, you will often see this notation, 0 with the plus sign in the superscript and 0 with the minus sign in the superscript. So what is 0 plus? 0 plus is a small positive number. That is, this number can be, for example, plus 0, 0, 0, 0, 0, 0, 1. That is a number that is almost equal to 0, however, it is positive. On the other hand, 0 minus means a negative 0. That is, 0 minus denotes a number that's negative and almost equal to 0. For example, this number can look like this. Minus 0.0001. Okay. Here's the main strategy for sketching the Nyquist plot. First of all, we are going to sketch the Nyquist plot by varying omega in the interval from 0 plus to plus infinity. Then, to obtain the graph for omega in the interval from minus infinity to 0 minus, we will simply mirror the graph obtained for omega in the interval from 0 plus to plus infinity with respect to the real axis. That is, the Nyquist plot obtained for the negative values of omega is simply obtained by mirroring the Nyquist plot for the positive values of omega. And in the third step, we are going to resolve what happens when omega is in the interval from 0 minus to 0 plus. That is, we will need to use our semicircle that we explained previously. To sketch the Nyquist plot, we first need to construct a table of characteristic values of omega and the corresponding values of real and imaginary parts. So let's construct the table. The first column of the table will contain the values of omega. The second column of the table will contain the corresponding real parts. And the third column of this table will contain the corresponding imaginary parts. Over here, I will construct the coordinate system and the complex plane that will contain our Nyquist plot. Here's the real part, and here's the imaginary part. Let's start with omega is equal to 0 plus. When omega is equal to 0 plus, the real part is equal to minus 1. And the imaginary part is approaching to minus infinity. Consequently, over here, we can sketch the point. This is minus 1, and the imaginary part is minus infinity. I will denote this point over here. And this is the point obtained for omega is equal to 0 plus. Next, let's select any other value of omega, for example 1. When omega is equal to 1, from this expression we can see that the real part is minus 0.5, and the imaginary part is also minus 0.5. Consequently, over here, we have this point here. And this point is obtained for omega is equal to 1. So let's select the next point at infinity. The real part is obviously 0 minus, and the imaginary part is 0 minus. However, by analyzing these two expressions, we can observe that for very large values of omega, this term in the denominator of our imaginary part will be much larger than the corresponding term in the denominator of the real part. And this is the case for large values of omega. Consequently, our graph will look somehow like this. It will go like this, this. Omega increases, goes to 1. Then omega goes further, and when it goes to infinity, and let me sketch the complete branch. Here it is. This is the branch of the Nyquist plot when omega goes from 0 plus to plus infinity. And over here I will denote the point omega is equal to plus infinity. Next, the main question is, what happens when omega goes from minus infinity to 0 minus? Well, to obtain these values, we will simply mirror this branch of the Nyquist plot with respect to the real axis. And as the result, we will obtain the graph that looks like this. This point will be mirrored over here. This point will be mirrored somewhere over here. And again, we can connect everything. Here it is. And then let's make sure that the other parts are also mirrored properly. Here it is. And let's make this line to be a little bit thicker. And that's it. We are almost there. Here it is. Looks beautiful. Now, over here, this point is omega is equal to 0, but minus now. This point over here is omega is equal to minus 1. And that's it. Next, it's a good practice to add arrows. These arrows denote how our graph changes when omega goes from 0 plus to infinity, and when omega goes from minus infinity to 0 minus. Obviously, we go like this. However, the Nyquist plot is not complete. Namely, we are missing the third branch. This third branch will tell us how do we transition from omega is equal to 0 minus to omega is equal to 0 plus? Obviously, for omega close to 0, either from the left or the right side, we are somewhere at infinity. That is, we are somewhere over here. So, do we transition from here, like this, to omega 0 plus, or we do somehow like this? This is a very important problem that we need to solve. The transitioning and this circle has an important implication on the stability of the system, and consequently it's very important to properly sketch this transition. To sketch this transition, we need to go back and we need to start from our transfer function. Our original transfer function had this form: 1 over s multiplying s plus 1. At the beginning of this video tutorial, we performed this substitution: s is equal to j omega. And as we explained, this substitution is not valid when omega is equal to 0. This was mainly because for omega equals to 0, we have a singularity over here. That is, the value of the transfer function becomes infinity. And that's precisely what we see over here. Now, when we are close to 0, we are going to use a different substitution. To illustrate this substitution, I will sketch another graph. Here it is. Over here is our original imaginary axis, j omega. And here is 0. When sketching this graph, we varied omega from minus infinity, and then we went up the imaginary axis. We went up until here. This is 0 minus, and then we sketched the graph from here, that is from 0 plus. And here it is. And that's precisely what you can see over here. This branch, or this part of the original imaginary axis, is mapped over here, and this branch of the imaginary axis is mapped over here. Now, instead of going through 0 along the straight line that's on the imaginary axis, we are going to divert. We are going to do this. We are going to go along a semicircle whose radius is equal to epsilon, where epsilon is a very small number. That is, epsilon is almost equal to 0. Or, using our notation, epsilon is equal to epsilon plus. Now, the main question is how to parameterize this semicircle. That is, what should be the substitution for s when s belongs to this semicircle? That is, what is the mathematical form of s? Well, the mathematical form of s is actually epsilon multiplying e to the power theta j, where theta j is the angle or the argument of s. So, what is the graphical interpretation of this formula? Now, over here, I'm going to zoom in and represent this circle. Here it is. Then I have semicircle. Then I have this part over here. Or let me draw it a little bit nicer, such that it really looks like a semicircle. Here it is. S is over here, for example. Epsilon multiplying e to the power theta j. Theta is actually this angle. This is theta. And epsilon is this distance from here to 0. Again, this is a zoomed version of this circle. And now you start to appreciate this parameterization. When we are close to 0, our s will not be j omega. Instead, it's going to be epsilon multiplying e to the power theta j, where epsilon is a very small number and theta is the angle. Over here, theta goes in the interval from minus pi over 2 to pi over 2. The point minus pi over 2 is given over here. That is, here theta is equal to minus pi over 2. And this is precisely the point 0 minus. Over here, theta is equal to pi over 2, and that's precisely the point 0 plus. Next, let's perform this substitution. That is, in the vicinity of 0, s is equal to epsilon e to the power j theta. If we substitute this value of s inside of our transfer function, we obtain t is equal to 1 over epsilon e to the power j theta multiplying epsilon multiplying e to the power j theta plus 1. Next, we obtain, if we multiply all the terms in the denominator, we will obtain epsilon squared multiplying e to the power 2j theta plus epsilon multiplying e to the power j theta. And here comes a very important analysis. Since epsilon is equal to epsilon very small value, we have that over here epsilon squared is approximately 0. And we can neglect it. Consequently, our t can be approximated like this. 1 over epsilon e to the power j theta. Now, this expression can be written like this. 1 over epsilon e to the power minus j theta. And this is a very important expression. From this expression, we conclude that the modulus, which is also known as the absolute value or the magnitude of our transfer function, is equal to 1 over epsilon. That is, m is equal to 1 over epsilon. Similarly, we conclude that the argument, which is also known as the phase or the angle of the transfer function, is equal to minus theta. That is, the modulus is denoted by m and it's equal to 1 over epsilon, and the phase denoted by phi is equal to minus theta. To conclude, when our s is parametrized such that it lives on this semicircle, our transfer function can be approximated like this, with the modulus given over here and the phase given over here. Next, let's verify consistency of this calculation as well as the accuracy. Namely, these expressions should be in agreement with the shape of this graph, and let's verify that. First of all, since epsilon is very small, magnitude is large, and that's precisely what we see over here. Namely, over here the magnitude is infinity as well as over here. And this is good. Let's verify that the phase is okay. First of all, theta over here is equal to minus pi over 2. This point is actually mapped over here. And let's compute the phase over here. From this expression, we can see that theta is equal to minus pi over 2. This implies that phi is equal to pi over 2. And this is consistent with this graph, since the phase over here is pi over 2. Of course, from this graph it doesn't look like this, but you should keep in mind that this point over here is at infinity, and consequently it's very close, or if not completely, on the imaginary axis. And consequently, the phase will actually be pi over 2, since this point is at infinity. And this is precisely what our equation is predicting. So this point is mapped over here, and this is okay. How about the second point, this point over here? For this point, theta is pi over 2. So when theta is pi over 2, we can conclude that phase is minus pi over 2. And that's precisely what's happening over here. Namely, the phase of this point over here is minus pi over 2. And again, keep in mind that this is at infinity. That is, it's going to be close to this part, to the negative part of the imaginary axis. And for the negative part of the imaginary axis, the phase is actually minus pi over 2. So everything is consistent. Okay, to summarize. When we reach this point, we are actually over here. And when we reach this point, we are actually over here. Now the question is, how do we transition on this graph when on our original graph we go along this path? Do we go like this? Or let me sketch it nicer. Do we go like this? Or do we go like this? Let's find out. Well, this equation will help us to figure out how we move. Let's see. When theta is minus pi over 2, that is when we are here, we are here. Okay. Now, what happens when we reach over here this point? Where is this point mapped? Let's see. For this point, theta is equal to 0. So let's denote theta is equal to 0 over here. Now, from this equation, we can see that phi for this point is 0. And 0 phi is over here. And this is a very important conclusion. So we have the first point and we have the second point, and this enables us to conclude this. We are transitioning like this. So we go here, and then from here we go here. And here is the direction. So we go like this, like this, like this, like this, like this, like this, and eventually we will reach 0 plus. So to summarize, when we move along the semicircle, we are actually moving along this circle with an infinite radius, and we are moving clockwise. And to verify this, you can choose another point. For example, over here we can select the point theta is equal to pi over 4. For theta is equal to pi over 4, from this equation we get phi is equal to minus pi over 4, and that's precisely the point somewhere over here. Consequently, the point over here is mapped into the point over here, and this means that from this point we go along this path, that is along clockwise direction. Okay, that's all for today, and thanks for watching.